Have you ever wondered, does a black hole live forever or does it have an expiration date? It's a common belief that once a black hole is born, it's here to stay, existing indefinitely, seemingly immune to the passage of time. Yet the reality of these cosmic behemoths may be far more fascinating and complex than we ever imagined. So do black holes truly possess an eternal lifespan? Well, the answer to that question might surprise you, as it involves a peculiar phenomenon called Hawking radiation. To grasp the concept of a black hole's death, we first need to understand Hawking radiation. This idea, as the name suggests, originates from the brilliant mind of physicist Stephen Hawking. He proposed this theory, not in a laboratory with high-tech equipment, but on a simple piece of paper with equations that describe our universe. Imagine being at the edge of a black hole, the boundary we call the event horizon. Here, a fascinating dance of particles is happening. This dance is based on the principles of quantum mechanics, the physics that governs tiny particles. According to these principles, pairs of particles and antiparticles spontaneously pop into existence and then annihilate each other. These pairs are known as virtual particles because they exist for an incredibly fleeting moment before they disappear. But what happens when this fleeting dance occurs near a black hole? Well, if one of these particles falls into the black hole and the other escapes into space, they can't annihilate each other. The escaping particle becomes real, stealing a tiny bit of energy from the black hole in the process. This is what we call Hawking radiation. Now, this isn't a fast process, it's like trying to empty an ocean with a teaspoon. The radiation is so weak that for most black holes, it's completely overpowered by the cosmic microwave background, the faint afterglow of the Big Bang. But theoretically, given enough time, and we're talking time scales much longer than the current age of our universe, a black hole could lose all of its mass and energy through this slow, steady leak. So, Hawking radiation in essence is a slow leak of energy from a black hole, a process that theoretically could lead to its eventual demise. Now that we have a basic understanding of Hawking radiation, we can delve into how it contributes to a black hole's death. Imagine a black hole as a cosmic beast, incessantly feeding on the surrounding matter and energy. But even these colossal entities don't last forever. They die, not in the way living organisms do, but through a slow and painstaking process of evaporation. Now, how does this happen? Enter Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in the mid-70s. According to this concept, a black hole can lose mass over time, a process akin to evaporation. Picture the event horizon, the point of no return around a black hole. At this boundary, pairs of particles and antiparticles spontaneously pop into existence, a phenomenon allowed by the quirky laws of quantum mechanics. Usually these pairs annihilate each other almost instantaneously. But sometimes one particle falls into the black hole, while the other escapes into space. This escaping particle, detected as Hawking radiation, carries away some of the black hole's energy, causing it to lose mass over time. Now you might think, well, black holes are always gobbling up stuff, won't they just regain this lost mass? Not necessarily. A black hole's diet mainly consists of cosmic dust and gas, which are not always in abundance. If a black hole is isolated with no nearby matter to feed on, it will lose more mass through Hawking radiation than it can gain, leading to its gradual shrinkage. This process, however, is not swift. It's slower than the drip of a leaky faucet in a drought. A black hole takes an inconceivable amount of time to evaporate completely. We're talking about time frames that dwarf the current age of the universe. So, contrary to popular belief, black holes can die, although the timescales involved are vastly larger than the current age of the universe. So, let's recap what we've learned so far about the life and death of a black hole. First and foremost, black holes don't meet their end in the way we conventionally perceive death. Instead, these celestial giants lose mass over time, a process known as Hawking radiation. Named after the brilliant physicist Stephen Hawking who first proposed it, this radiation is a theoretical prediction that black holes aren't entirely black, but emit small amounts of thermal radiation due to quantum effects near the event horizon. If this is indeed true, then black holes aren't eternal, and will gradually shrink and ultimately vanish. It's vital to remember, though, that Hawking radiation is purely theoretical. While it's part of the scientific consensus because it combines elements of quantum mechanics and general relativity, it's yet to be observed directly due to its incredibly weak nature. It's like trying to spot a firefly in a fireworks show. The energy that black holes release into the cosmos through other means, such as accretion disks and jets, vastly outshines any Hawking radiation. Now let's talk about the timescale. If a black hole could eventually evaporate, how long would it take? Well, it's hard to comprehend, but the evaporation period for a black hole is far longer than the current age of the universe. For a black hole with the mass of the Sun, we're talking about a timescale of 10 to the power of 67 years. That's a 10 followed by 67 zeros. For supermassive black holes, the ones that reside at the center of galaxies, the timescale is even more mind-boggling. And finally, we must reiterate that all these concepts are hinged on our current understanding of the laws of physics, which is continuously evolving. There are still many unknowns in our exploration of black holes and the broader universe. This is what makes studying them so fascinating. They are like the ultimate riddles of the cosmos, pushing the boundaries of what we know and understand. So while we may never witness the death of a black hole in our lifetime, the fascinating science behind it certainly gives us plenty to ponder about the mysteries of our universe.